A couple of reminders. The first homework is available now. If you go to either, actually, let me quickly show you. If you go to my courses or Canvas page and go to 426. I'm just showing the student view, so you can access the homework, either go to modules and click on homework 1 there. That will take you to an external website. So click on that. That will take you to the homework page. Or you can just click on the home page and then click on week 1. At the bottom of week 1, there's a homework link. So a couple of ways to get there. If you haven't done this yet, definitely check out the homework. Great. Apparently that doesn't work. Let me leave student view and so you're probably not going to see that page, but you're going to see something like this, and you can click on the homework one and start working on it. I give you 1 week, so it's due Thursday, next Thursday at 12 p.m. at noon. So so definitely start working on it early. I give you 25 problems, 1 point each. Some of them will be easy, some will be difficult. Just go through them step by step. If you run into problems, don't panic. You can email me for help, or you can go to the Mac Center for help. So definitely start working on those problems. Some of them you have to enter an exact answer. For example, if you get an answer pi over 6, you have to type pi over 6 instead of putting that into a calculator. So just be mindful about that. So if you put like what's pi over 6, I don't know. It's like if you put 0.5, it's not going to recognize as a solution. You have to type pi over 6. Remind on that. The second one is the quiz 0 is due Wednesday, I believe. Double check that deadline. It's really just scanning a few pages. You can use your textbook or any books that you have or notebooks. Doesn't have to have content in it. It could be like a blank pages, right? And then just scan 5 pages. I'll take a look at that. If you didn't do it correctly, I'll ask you to submit again until you get it right. So, any questions about the homework under the quiz 0 there?
Call from United Server. Call from United Server.
We don't have. Sorry, I don't know. I have a. Let me turn off this stupid phone. Sorry. So we don't have class on Monday. I'll see you on Wednesday. All right. On that note, I'm going to just get going with what we didn't finish last time. So last time I had a few examples I finished. So I'm going to start with those, which is the u-substitution. All right, I think my computer, hopefully it doesn't freeze. Let me close those windows. All right, here we go. All right, hopefully you can all see the notebook I'm sharing. Right, so yeah, so next week we only meet Wednesday and a Thursday. On Thursday, we're going to have a quiz. And I'll tell you what the quiz will cover probably early next week. So the first example I have here is from the worksheet from yesterday that we didn't get to finish. So we are integrating sine squared theta d theta. So here it's not straightforward because if you try to write as sine times sine, I'm going to erase this in a second, so you don't need to write down this part. So if you write as sine times sine d theta and I call one of them u, it doesn't help you there. So that's not a good approach. So the trick here is that actually to use a trig identity to rewrite sine squared theta. So if you recall double angle formula from trigonometry class, so cosine 2 theta is equal to 1 minus 2 sine squared theta. So that's just the double angle formula that you studied it before. So from here, we can solve for sine squared theta. So that will be 2 sine squared theta is equal to 1 minus cosine 2 theta, and then divide by 2. So you get, so that's a 2. So we're going to divide by 2, divide by 2, divide by 2. So we get sine squared theta is equal to 1/2 minus 1/2 cosine 2 theta. So that's the trick we're going to use to substitute for sine squared theta first before we integrate. So every time you're integrating sine squared theta or cosine squared theta, think about one of those think about this double angle formula. That's going to help you. So I'm going to put in there. So this integral becomes integrating 1/2 minus 1/2 cosine 2 theta d theta. And from here, I'm just going to separate the integrals, make it becomes 1/2 integral just 1. If we're integrating 1/2, we bring half to the front, d theta minus 1/2 integral cosine 2 theta d theta. The first term, I'm pretty confident that all of you can integrate 1 with respect to theta at this point. The difficult part is this second term with a cosine 2 theta there. That's the part that we have to use substitution because we know how to integrate cosine theta, or cosine x, but we don't know how to integrate cosine 2 theta. So that's the difficult part. So we need substitution here. So how do we substitute this? So if you look at the cosine function, you have cosine 2 theta, right? So the inner function looks like a 2 theta. How do you get the first term? So the first term I did is so I basically sort of integrating each term there. So this term coming from integrating 1/2 d theta. So that's how I get the first term. So I just bring the half in front of the integral. And this second term coming from integrating 1/2 cosine 2 theta. That's what this term is. So now I'm going to let u equals 2 theta. So du equals 2 d theta, and solve for d theta there. So d theta equals 1/2 du. And I'm just going to focus on the second integral here. The first one I know it's fairly straightforward. So the second integral, if we integrate cosine 2 theta d theta, using the substitution, we can rewrite this as integrating cosine 2 theta is u, so cosine u, and d theta is 1/2 du. So that becomes 1/2, bring the half in front again. So we got 1/2 integrating cosine u du. And this part we know That's 1/2. If you recall that when we integrate cosine, we get sine, right? So that we get sine u there. And obviously we have to add a constant c. And then don't forget to rewrite sine u as sine u is 2 theta, so sine 2 theta plus the c. So this expression is the integral part in the second part. Is the integrating cosine 2 theta d theta. Okay, here's a question. What happened to the other half? Okay, so I did not touch that yet. That's a good question. So the half in front of it, I'm just going to just leave it there for now, and then I'm going to use it in the next step. So this half, I did not use it at all, so it's still here. And we're just going to multiply with whatever we got later. So now I'm going to rewrite this part. So the first term give me half, and the integrating 1 with respect to theta, I get theta. So 1/2 times theta, right? And then obviously I'm going to add a constant c. I'm going to call it c1. You don't have to worry about the c1 here, but just there's a constant. And then I'm going to minus, remember there's a half there. So this half now I'm going to bring it down to use it. So this give me half times the integral of the cosine 2 theta d theta. So that will be 1/2 sine 2 theta plus a c from the second integral. And the rest is about simplifying. You probably wonder, that's a lot of constants. Well, let's put all the constants together. So I got 1/2 theta plus c1. I'm going to move it at the end. So plus a c1, move it to the end. And then I have minus half times half sine. So that's a minus 1/4 sine 2 theta. And then so that's distributing the negative half. Then I distribute again to the c. So that will be minus 1/2 c. Okay. So at this point, I want to show you, doesn't matter what c and the c1 is, right? So those are the constants. So if you multiply them with numbers and add them together, you still end up with constants. So we're just going to rewrite this terms with c and c1 with just a constant c. So we just write 1/2 theta minus 1/4 sine 2 theta plus a constant c. Obviously, this c is different from the c we used before, but it's a constant. Questions on this problem? I just want to point out the very first thing we did, that's just a trick. There's no particular reason. Well, the reason is that we have to use it so that we can integrate. But other than that, this part is not calculus, it's just a trigonometry. All right, so where did the negative 1/2 c go? So I combine the negative 1/2 c with the c1 because c is a constant, c1 is a constant. So if I multiply c with negative 1/2 plus a c1, it just together they are a constant. They represent a constant. So I just use a new c. You can call it d if you like. I use a new c to represent that expression, the constant term. This is also another thing you can use in the future is that when you integrate multiple parts, you don't have to add a c. You just make sure that at the end you add a c at the very end. So you don't have to. So here I added this c. I don't have to add this. I don't have to add c1. It just as long as I keep a c at the very end, it's still correct. Not always the case, but for now it is. Can we move on? All right, so the next question I have is we're integrating cosine 2x divided by 1 plus sine squared 2x dx. This term, if you ever have 1 plus some term squared in the denominator, you always want to, this should look, you always want to use substitution so that this looks like some term and have 1 plus u squared in the denominator. So that's what we try to achieve. Aiden, yes, that's correct. So the -1/2 c plus c1 together just give us some constant that we don't know. So if you have some, so number 2, you always want something like that. So the substitution is that the denominator has a sine squared 2x. So this term is the same thing as sine 2x squared, right? So the sine 2x is the inner function that we're going to call it u. So using substitution, so we're going to let, so we're going to let u equals sine 2x. And then take the derivative, so du coming from the u. And then when we take the derivative of sine 2x, we have to use chain rule there, right? So sine, give me cosine. When we take the derivative, so that's cosine 2x. But then we have to take the derivative of the inner function of sine 2x, which is the derivative of 2x, is 2 dx. And I'm going to solve for dx. So dx will equal to 1 over cosine 2x times 2, so -1, so 1/2 cosine 2x, and then du after we solve for dx. And now I can go back to the integral and substitute for sine 2x and also substitute for dx. So this integral becomes integrating cosine 2x divided by 1 plus sine squared becomes u squared. That's good, right? That's what we needed. And the times dx, which is 1 over 2 cosine 2x du. And it's really nice here because the cosine 2x and then the cosine 2x in the denominator cancel, give me 1. This give me integral. There's a 1/2 side, so I'm going to bring the half in front of the integral, right? So this half, I'll just make it more confusing there. So this half, I'm going to bring the half in front of the integral. So that goes in front of it. So just give me 1/2 integrating 1 over 1 plus u squared du. If you, I don't know if you have a chance to look at the table on page about like in section 5.5 or maybe 5.4. That's whenever you integrate 1 over u squared, it's always going to give you inverse tangent, I believe. So we get 1/2 inverse tangent of u plus a constant c. And then the very last step, don't forget to substitute for the u. So we get 1/2 inverse tangent of u. U is what we call sine 2x. So sine 2x is inside inverse tangent plus a constant c. Obviously, don't worry about simplifying at the end. You know, this is perfectly acceptable. There's no need to go further to simplify. Any other questions? All right, if you forget, this is on page 410. It's from the table with all the integrals, the common integrals. I got ds, but what about putting dx into the equation? So you got dx, right? So literally take this, take this expression and then go back to the integral that where you see dx, you substitute for the dx there. So that's why I got this part. So that expression replaced dx. And then after you've done that, the cosine 2x will cancel and it'll give you 1/2, but you can bring half in front of the integral. So yeah, so that's what I always do. I always solve for dx. Even though you take the derivative, you get du, but it's a dx, that's the part you want to replace in the original integral. And then simplify. All right, so the next question I have is we're integrating x minus x cubed divided by 1 plus x to the 4th dx. This expression is not straightforward, but at least just by looking at it, right? In the denominator, I have a 1 plus x to the 4th. So perhaps I can somehow make it look like we did before. So every time you have a 1 plus in the denominator, you can always try to, doesn't mean it's always going to work, but you can try to rewrite this as some expression divided by 1 plus u squared du, right? So just that will give us inverse tangent. That's something we can try. So if that's what we want, that means u, we can try to, so try let u equals x squared, right? Because we get x to the 4th. So if we want that to be u squared, so u has to be x squared. So let's try that. Du will be 2x and then dx. And I'm going to solve for dx. So dx equals 1 over 2x du. So now I'm going to use substitution into the integral we begin with. So we get integral x minus x cubed divided by 1 plus u squared. And then I get 1 over 2x du. You probably look at it as like, doesn't really help us much, a little bit. The denominator has the x, and the numerator has x minus x cubed. So maybe we can simplify the numerator with the denominator with the x terms, right? Because there's an x cubed, so we can try to simplify the x. So factor out x from the numerator, so we get x 1 minus x squared divided by 1 plus u squared times 1 over 2x du. Now I can simplify the x term. So this cancels. It gives me integrating 1 minus x squared divided by 1 plus u squared. And then I have half, but the half, I'm going to put it in front. Don't worry about the half du. So it looks like it's simplified a bit. Why can't you just get rid of the first x in the numerator? You mean like cancel with the x in the denominator? Well, in order to cancel with the x in the denominator, you have to factor out the x first from the numerator. You cannot just simply, you cannot just cross out this x with this x, because this first x, you have to factor first from this term. So this term, you have to take out x to get this, and then you can cross out the x. All right, so we're getting close, and from here we still have an x and a u, so that's not very good, right? When we integrate, we just want u or just x. We don't want a mix of them. So now, if you recall that we start with u equals x squared, so maybe we can substitute for this x squared. That will help. So that will be 1/2 integrating 1 minus u divided by 1 plus u squared du. And this still doesn't help us much. We still get this complicated expression. it's so from here, the trick that we're going to use is we're actually going to separate it as two fractions that we want, two functions that we want to integrate. So the half, I'm going to leave it, but I'm going to separate the fraction so it becomes integrating 1 over 1 plus u squared du, and we know what that is. Right, we saw that earlier in the previous problem. And then I'm going to add a bracket here. And then we have minus u integrating u over 1 plus u squared du. You probably wonder, how does that going to help us? Well, at least the first part, we have this. So this part we know. Let's give us inverse tangent of u based on what we did in the previous problem. But how about the second one? Any suggestions at how could we integrating this part, the second integral? Would it be u times arctan? Oh, no, actually, that's a good guess. But no. So when you integrate, you cannot just pull out the u. So the u is actually, the function depends on u in this part. So the u cannot go outside. So that just doesn't work. So you kind of have to integrate this function. You actually know how to do this. So from here, we just have to use substitution again. Because if you look at it, the u in the numerator is sort of the derivative of the u square, right? So this is kind of the derivative. Of the denominator. So what we're going to do is we're going to use substitution again. So this part use substitution. So we're going to let 1 plus u squared equal to maybe v or w, depends on just some variable. And then dw is equal to 2u du. And just like we did before, we solve for dx. So here we're going to solve for du. So du is equal to 1 over 2u dw. And then I'm just going to focus on this integral here, just a second integral. So I'm going to use substitution. So I'm integrating u, it's just a u in the numerator, but the denominator is become w. And then du becomes 1 over 2u dw. And the benefit of using the substitution is that the u in the numerator and the u in the denominator, they cancel. And if we keep integrating, we get integrating 1/2. We get a 1/2 from this substitution. And then we have 1 over w dw. And then you know how to integrate the 1 over w dw, which is natural log. So that gives us a 1/2 natural log of absolute value of w. And obviously we're adding a c. I'm going to call it c1. Let me move this to the side just so that I'm going to call that c1. And then the first integral. So now we finish integrating the second part. The first part we also integrate, we get inverse tangent of u plus a c2. You can call it a constant c2. So now I can put them together. So this integral, we're integrating, so that becomes a 1/2. We still have a 1/2 in front bracket. And then the first term give me inverse tan of u plus c2. The second term, so minus, the second term give me 1/2 natural log of absolute value of w plus c1. There's a lot of terms, but if we just, kind of step by step, keep the work organized, we should be okay. And then the rest is about rewriting this. This is what we get after we're integrating. This is the antiderivative, but it's not correct because we still have a u, we still have a w, we have to substitute for them. So the next step is about simplifying and substitute for u and a w. So I'm just going to simplify this. So I get 1/2 bracket inverse 10. The u, what is u? U is x squared. Right, I had a u is x squared here, so we still got to use that, put it back into the antiderivative at the end. So u is x squared. C2 is just a constant, so plus a C2, I can put a C2 here at the end. Inside the bracket, I'm still working inside the bracket. And then I have minus 1/2 natural log of w. What is w? W is 1 plus u squared, so that's 1 plus u squared, absolute value. And then plus a c, minus a c1, so minus a c1. And the minus c1 plus c2, you can call that a new constant, c. So the next step, I'm going to distribute the half, and I'm going to substitute for the u again. So I have 1/2 inverse 10 of x squared minus 1/4 natural log absolute value 1 plus u squared. Recall u is x squared. So x to the 4th power. And then we have 1/2 times negative c1 plus c2. And this term is a constant, so we can just call it c, like some c. The step lag in half next to natural log, I saw by half out already. Well, let me kind of show you this. So the half that we take out, this half, it coming from earlier. So that half multiplies the entire integral, right? So that half multiplies this expression. And then that integral, if we separate it, it becomes those two parts. The half, we took it out earlier, that's still just outside, right? And then you talk about this half coming from integrating the second integral, coming from there. So if we integrate that, we get half. So this half is different from the half we had earlier. There's a lot of halves, right? But it's different parts. Okay. Any other questions? All right. All right. So that's just finishing what we didn't finish last time. So if you don't have any questions, I'm gonna move on to the next part. But let me give you a few seconds, just maybe process this problem. All right, the next part is it's a u-substitution, but with definite integrals. You can follow what we did before, but you can also take another approach. So the definition from the book, I'm just going to write it here. So if we're integrating from a to b of f of g of x, g prime of x dx, that you can write, recall that for indefinite integral, we call this part u, right? And the g prime dx becomes du. So we end up with f of u du. That's the expression we had for indefinite integral. But the tricky part here is that the a in the given part, that's the x value, right? X is going from a to b. The b is also x value. But when we end up with a function of u and a du, before we substitute for x. So here in this integral, if you want to end up with f of u at the end, right? Evaluate it at two numbers. It's not a and a b anymore because a, if we replace x with u, then a is not the boundaries anymore. So here we have to find the new boundary, which is g of a and g of b. Those are the new boundaries. The boundaries change when we replace x with u. So the boundaries are not the same anymore. I'm going to use one example to show you that you can use this approach, or you can just use something else. So this is a one way. The second way is actually, I actually prefer because it's much closer to what we did before. So the second approach is that we can always take f of u and then rewrite it as f of x, maybe not f of x, like f hat of x, right? If we substitute for u there, we get x. And then from here, we can plug in a and b directly. So this is the second way. Most of the work is still the same. It just depends on when you want to plug in the values and which values you're going to plug in. So either you work with function of u, plug in the new boundaries, or you work with function of x, plug in the same boundary that was given. It's completely up to you, but I'm going to show you how to do that using examples. All right, that's a problem with what I did with this example. So this example, I forget to put x squared there. Oops. Okay, so I forget to put x squared in that expression. All right, so let me use this example, number 4, to show you what I meant there with two ways. The very beginning, the most of the work is the same. It just towards the end is a bit different. So with example 4 here, I have this function of x, and then remember, keep in mind that x, this -1 is the x value, 1 is also an x value. It's not value for u, just for x. So from here, I'm going to use substitution. I'm going to call this x cubed plus 1. So I'm going to let x cubed plus 1 equals u. And the du will be 3x squared dx using chain rule. And the solve for dx, so dx is equal to 1 over 3x squared du. Now I'm going to put the substitute for dx and the substitute for x cubed plus 1. So this integral becomes -1 x squared square root of u times 1 over 3x squared du. But keep in mind that this -1 is the x value. 1 is also an x value. It's not a value for u. And now I'm going to simplify the x squared. I'm going to simplify the x squared there. So I'm going to bring, and then I'm going to bring 1/3 in front of the integral. So I have integral from -1 to 1 of square root of u du. I hope you agree with me there. And then from here, I can rewrite u, square root of u as u to the half to make it easy to integrate. But keep in mind that those are the x values. So the next step, when I integrate, finding the antiderivative of u to the half, I get u to the 1/2 plus 1 is 3/2, right? But then I have to divide by the new, sorry, I forgot a 1/3. Yeah, sorry about that. So I still have 1/3 in front of it. But then I have to divide by the new exponent, so divide by 3/2. And then plus constant c, but we don't need that because this is a definite integral. So we're evaluating this expression from x equals -1 to x equals 1. Simplify it a bit. So we get 1/3 divided by 3/2. So we get 2/9 of u to the 3/2, evaluating from x equals -1 to x equals 1. But I cannot plug in the x value. I have to get a function of x. So now I have to substitute for u. So we get 2/9. What is x? U is x cubed plus 1 to the 3/2. Now I can evaluate this from x equals -1 to 1. So now I'm going to plug in 1 and a -1. So I get 2/9. 2/9 is a factor, so I'm going to put it outside. So plug in 1, so I got 1 cubed plus 1 to the 3/2 minus plug in -1, so I get -1 plus 1 to the 3/2, which can be a 0. And the rest I can finish it by calculating the first term. 2/9 times, that's a 2, so square root of 2 cubed. Right, so that's this is a 2/9 times 2 to the 3/2, which is a square root of 2. 2/9 times square root of 2 cubed, so that's a 2 square root of 2, which is 4/9 square root of 2. This term becomes a 0 because the -1 plus 1 is a 0. So that's the way I prefer to do. But this is a second way. This is not the first way. The first way says, at this point, after we get the or maybe this point, after we get an expression for u, we can just leave it. We don't. How do we do to make that compatible there? Let me scroll up. So this is the second way that we did, right? Get a function of x, plug in the x values. But what's the first way says is that when we get to this point, the one I'm writing in purple, when we get there, instead of plugging x value, we can find out the new boundaries. So from here, we're going to find boundaries for u using x. So at x equals 1, u equals, recall that u equals x cubed plus 1, right? Yeah. So we can solve for u, plug in 1, so that's give me 2. And at x equals -1, we can solve for u, which is -1 cubed plus 1, which is 0. So we have, instead of using the x boundary -1 to 1, we can use 0 to 2 as a u boundary. So this part will become 2/9 u to the 3/2 evaluated at from 0 to 2. So those are the u values. So it's okay to plug in directly. So now we plug in directly, so we got 2/9 of u to the 3/2, which is 2 to the 3/2, minus 0 to the 3/2, which is a 0. So we still end up with 2/9 times 2 to the 3/2. And then if you do all the work, you end up with 4/9 square root of 2. I just want to show you that those are the two approaches. Whichever you prefer, remember that definite integrals give you numbers, right? We want a number at the end. So whichever approach that you find it easy, you can use it, but at the end, you always want to end up with just a number. Some people find this approach easy, and some people find the one on the left easy. But I'll let you decide. Two to the 3/2. Okay, that's a good question. So the next part, I'm going to quickly explain how to rewrite 2 to the 3/2. So 2 to the 3/2, the number in the denominator means roots, and the number in the numerator, in the exponent, the number in the numerator means power. So the 2 to the 3/2 becomes 2 cubed, and then the 2 in the denominator become a square root. So that's a square root of 8, which is 2 square root of 2. That's a good question. Will there ever be a case where the two methods would give us different answers? No, you shouldn't have that case. Right, exactly, Aiden. Yeah. Oh, right. If you have, because both methods are legit, right? They're equivalent. So if you end up with different answers, that's, yeah, that shouldn't happen. Good. Just be careful. You know, we all make mistakes when we're solving problems, right? There's like a lot of places to make mistakes, but just what I find out to be helpful is that I like to keep all the steps. So I don't try to do everything. Well, sometimes I do it in my head, but I try to write down all the steps so that at least I can go back to check, make sure every step is right. I have something to look back to. And also just be mindful, right? When you do some algebra, adding numbers, subtracting numbers, or canceling, just be mindful. You should be better. I just put it that way. Just be careful. So that's this question. Shall we do another one? All right, I'm debating which one to pick. So the next example I have is we're integrating from 0 to 2 of x minus 1 e to the x minus 1 squared. So that's an exponent in e. So this one, can anyone tell me what? Obviously, I'm going to use substitution, right? What should I let u be? So using substitution, so we're going to let u equals what in this example 5? So we're going to pick an inner function, but which one should it be? Excellent, exactly. So we're going to actually let u equals this exponent of e. Because if we kind of just look at it, this front part looks like the derivative of the exponent. So we're going to let u equals that exponent, so x minus 1 squared. So du, using chain rule, right, will be 2 times x minus 1 times the derivative of the inner part. So the derivative of x minus 1 is just dx minus 0, so just dx. And then solve for dx. So dx is equal to 1 over 2x minus 1 du. Now I'm going to use substitution. So this integral give me from 0 to 2 x minus 1 times e to the u times 1 over 2x minus 1 du. And the benefit of this is that the x minus 1 and then the x minus 1 in the denominator, they cancel, give me 1. So under the half, I can bring it in front. So I get half integrating 0 to 2 of e to the u du. But keep in mind that the 0 to 2 are the boundaries of x, not u. So those are the x values. And then the next step is integrating. If you recall that e to the u will give you e to the u. And then we evaluating from x equals 0 to x equals 2. So now you can substitute for u with x, or you can just find the boundaries for u. So I'm going to take the second approach. I mean the first approach. So here we're going to find boundaries for u. So at x equals 2, we had u equals x minus 1 squared at x equals 2. So that's 2 minus 1 squared, which is 1. At x equals 0, we get u equals 0 minus 1 squared. Again, is a 1. Did I do it right? Yeah, I think that's right. And then we just end up right. So the answer will be 0. Will be 1/2 e to the u, evaluating from 1 to 1. So that just becomes a 0. Because if we put like a e to the 1 minus e to the 1, so that just becomes a 0. How do you feel about this substitution method? Okay, good. So you do have to kind of practice a lot. The more you work on it, the better you're going to get on those problems. All right, good. So I'm going to move on to the next problem. I'm not going to solve it. I'm just going to kind of get started. So here we're integrating cotangent theta cosecant square theta d theta. So anyone know what we should do? Which part should we call u, or should we do something to simplify first? Which one do you think should be the u here? No, that's actually a good trap to fall into. No, it's actually not cosecant theta. Right. It's actually, there's a couple ways you could approach this. You could, so if you recall that d dx of cotangent x is equal to negative cosecant square x, right? That's something you probably come across before. So this part looks like, even though it has a square, it's actually the derivative of the first term. So that's one way. So you can let u equals cotangent theta, and the du equals negative cosecant squared theta d theta. So solve for d theta. So d theta equals negative 1 over cosecant squared theta du. And then now you can put it in there, and it will cancel out the cosecant squared. We get, what is it? U times negative 1 over u times cosecant square theta times negative 1 divided by cosecant square theta d theta. And then those cancels out, and give you 1. So we just get negative u, you're integrating. I'm not going to finish it. It's you kind of have to be comfortable with trig. You have to know what cotangent pi over 2 is and a cotangent pi over 4. If you don't know that, I recommend that you look it up. So you probably have to use at some point cotangent of pi over 4. That's a 1 over tangent pi over 4, which is 1 over 1 equals 1. And at some point you will have to use cotangent pi over 2, which is 1 over tangent. That's not a good way to use 1 over tangent pi over 4. That wouldn't give you a good answer, but you have to rewrite this as, sorry, pi over 2. You have to rewrite this as cosine pi over 2 divided by sine pi over 2. That become a 1. No, become a 0. So at some point, you're going to use those two trig values in order to complete the problem. So that's all I have to say with substitution and the integration. Any questions? So I didn't finish this, but the rest should be manageable. All right, I'm going to move on to the next part, which is we're going to talk about symmetric functions. So if you recall that even functions, so if you have a function that's symmetric over the y-axis, so if you have a function looks like, so that's a symmetric function. That's an even symmetric function. So even function have even functions have y-axis as line of symmetry. What do we? There's a good thing about the symmetry here is that if we were to integrate this function, let's call it f of x. If we want to integrate from, let's see, from negative a to positive a of f of x dx, because of the symmetry, the left side of the area to the left side of y-axis, this area, is the same thing as the area on the right side, right? We're looking for the net total area when we integrate. So we can just say, okay, instead of integrating from negative a to a, why don't we just integrating from 0 to a, but only take, so that will be only half of it. We just need to double that part. So that's the same thing as 2 times from 0 to a f of x dx. For even functions, that's always true. The way I remember is I always think about, for even functions, the area to the left side of the y-axis is the same thing as to the right side. So if you just find one area, you multiply that by 2. And the next one is odd functions. So odd functions has a symmetry about the origin. So you can draw something like this. So odd functions have symmetry over the origin. So if you take it, rotate 180 degrees, you get the same graph, even though I didn't draw it correctly. That's what it is. And if we're integrating an odd function from negative a to a f of x dx, I'm going to draw this diagram here for this shaded region. So the left side of the origin and the right side of the origin, they have the same area in terms of magnitude. But the problem is that the left side is below the x-axis, so this part has a negative area. This part is a positive. So basically you have, for odd functions, you have one side is a negative, you have a negative area, the right side is a positive area. So when you take the negative and the positive, when you add them together, so that will be the integral, right, from negative a to a. So you should get a 0. This is very useful in differential equations if you're planning on taking it, if you're integrating a sine function. So this is like integrating from negative a to a of sine x dx, you always get a 0. Or you're integrating from negative infinity to infinity of sine x, again, you get a 0. But if the first case is like a cosine function, from 0 to, well, not negative. You know what? Let me take it back. Not, I gotta be careful with this. So let's just say negative pi to positive pi. The cosine function is negative pi over 2 to pi over 2. Anyway, so that's a benefit with working with even and odd functions. In high level math, there's a lot of functions that you can use sine and a cosine to estimate, and then when you integrate, some of the terms will go to 0. Some of the terms will stay. Anyway, so if you want to study high level math, it's we use a lot of sine and a cosine. Right. So with that said, so I'm going to go through one example. I have 2 prepared, but I'm only going to go through one because I don't have enough time. Because I want to finish at 7:50 today. That way, you get some chance to get some dinner. So here's the first example I have. It says find the net area between the curve and then given by the function f of x. So between f of x and the x-axis from 2 to negative 2 to 2. So we're basically looking for this area underneath the curve. Now, by just looking at the graph, this kind of looks like an even function. It is actually even function. You can double check that. So this is an even function because if we take f of negative x, put in there, if we find f of negative x, we should get f of x. So I'm not going to do the work to check it, but it is an even function. The net area is equal to integral from negative 2 to 2 f of x dx. So that's what net area between the curve and the x-axis give me. But instead of doing the whole thing from negative 2 to 2, I can just rewrite this as 2 integrating from 0 to 2, right? Because it's even, so I can just find the area on the right side and then multiply that by 2. That will give me the total area. So that will be integrating x to the 4 minus 4x squared plus 6 with respect to x. Now you might wonder, why do we do this? Like, what's the benefit of integrating from 0 to 2 versus from negative 2 to 2? Well, the benefit is that a lot of times if you plug in 0, you get 0, right? As a usual, well, not always, but sometimes, right? When you have like an x to the 4th or x to the 5th, you get, when you put 0 there, you can get 0 sometimes. So that will save some time. So that's sort of the benefit of doing this. So I'm not going to finish this because the rest is just integrating. I think we have done enough exercise to find the antiderivative and the plug-in numbers. But I just want to show you this. This is a second example. I'm not going to do it, but if we basically, if we were to integrating from negative 2 to 2 of this is an odd function because it's has a symmetry over the origin. before I even do anything, because it's an odd function, so if I integrate from -2 to 2 of f of x with respect to x, the fact it's odd function, this is a positive area. This part is a negative area. So the net area will become a 0 here. So the integral will become a 0. If you don't believe me, you can figure out do all the integration, you should end up with a 0. Any questions on that? All right, let me give you 1 minute to finish writing, and then I'm going to move on to the next section, which is finding area between two curves. Like any two curves that you can draw, you can find the area between them. All right, so area between two curves. You might wonder, why do we even care about area between two curves? Right, for example, if this is a function f, this is a function g, and why do we need to know the area between them? Well, it's in real life, a lot of times we have to calculate the area, right? We have to know how much the material or how much the cost is, that based on the area. So for example, if I have, let's say I have a, let's just say a flower. Not the prettiest flower, but let's say I have a flower. I want to know what is the area of this shape, right? Basic geometry doesn't help you because the boundaries are not rigid lines. It doesn't help you. But with calculus, we can say, okay, I'm just going to divide the curve using a few sections. For this part, I can calculate this area, because if I can fit a function in there, so I can find this function and then use this line, I can figure out this area. Or instead of doing that, I perhaps could draw a vertical line, divide it this way, so that I can use this curve if I know what the function is, and this vertical line, I can figure out this area. So you can divide it into a lot of areas that make it easy to calculate the area of each part, and then add them together to get the total area. That's what a lot of programming does to estimate area. Anyway, I just wanted to point out that probably not a good application, but that's what I was thinking. So let me write down the sort of the definition to find the area between curves. So here, when we talk about area, we mean not the net area, we mean the total area. Not net area. So suppose we have this region A between function f and the g. So suppose A is bounded between f of x and the g of x, and f of x is greater than or equal to g of x, or I probably should label this A, label this B, for all x between A and B. A and B doesn't have to be, the endpoints. Depends on the region. Then the area A will be given by integral from a to b of f of x minus g of x dx. I'm going to use a diagram to show you where this comes from. So this formula, this integral formula, coming from the idea that from the very beginning when we talk about integrals, you remember the Riemann sums, like the sum of all the rectangles, add them together. So suppose that we have, let's see, this is a x, this is a y. Suppose that we take this area, this section, we divide it into a lot of rectangles, right? There's a lot of them. Let's just focus on one rectangle here. This one rectangle, I'm going to call the base delta x. That's the base of the rectangle. And this part, this value is g of x. Let me use a different color. This value here. This value is g of, let's call this x. This delta, let me rewrite this. This base here is delta x. This value, I'm going to call it x. So this height here, this is g of x. And the height on from the top curve, the curve that's higher, this is f of x. So the height of the rectangle is given by f of x minus g of x, right? That's the height of the rectangle. And then the area for one rectangle, so area of one rectangle will be just base, delta x, times the height, f of x minus g of x. But if we add up all the rectangles together, so area total is equal to summation of from maybe I from 1 to n or infinity of this rectangles together. So that's a summation of f of x minus g of x delta x. That's a total area. But that's not enough. We have to take a limit as n goes to infinity, right? If you remember, that's a definition of Riemann sum. So we have to say, okay, that's infinitely many rectangles between that put together give you the region between the curves. Well, this is really the same thing as this. The dx is what delta x is, and the other part, the integral from a to b, you can think about as the limit of the summation. So I want to point out that this gives you the height of the rectangle. This part gives you the width of the rectangle. So if you kind of, I probably should write it here. So this is the height of rectangle. This is the width of rectangle. So if you take the height and then the width of each rectangle, you multiply them together, that will give you the area of one rectangle. But if you add all of them together, you get the total area. So that's integrating with respect to x. But I do want to point out that, so that's the case that if f is greater or equal to g, but there's also a second part to it. So suppose you have f is like this and the g is like this. So this is g, this is f. So this is the f. Suppose that part of it, f is greater than g, part of it is less than g. Then we need to find the intersection point and use and use the point. Let me replace this, and then we're going to use 2 sub areas to find total area. So if you have a case that the f, some part of it is less than g, some part is greater than g, so we're going to have to focus on each area separately. So we're going to find the first area using, so the total area here will be, let's call this A, this is B, let's call the middle point C. So we're going to have to focus on the area of the A1. So A will be equal to A1 plus A2, which is equal integral from A to C of f minus g dx. Then we're going to add the second part, which is integrating from C to B. Now, in the second part, in this part, this is f, that's g, so g is actually more than f. So the height of the rectangle, if you draw a rectangle there, the height is given from g minus f. So g minus f dx. So it's really the same thing we had earlier, but now you just focus on different sections of that region. Because the height of the rectangle is always given by the function up of, so the function higher minus a function lower. That will give you the area. Right, the height is always the high number minus the lower number. That will give you the height. All right, that might be a lot of information to take in, but let me use one example to kind of help you to get started. You know what? I do need to use this to show you. So when you work on a problem like this, it's always good to use decimals to graph the functions to get a kind of a picture, to know which area you talk about. For example, here the first part says, the first example I have is says, find the area of the region bounded between y equals 6 minus x squared and y equals x squared minus 4x. So what I'm going to do is I'm going to open decimals. I hope that you use it before. If you haven't used it, it's called desmos.com. And then just go to the graphing calculator. From there, you're just going to type down the 2 functions. So the first function I have is y equals 6 minus x squared. So that will give me a curve. And then the second function is y equals x squared minus 4x. So let me move this. So now I put those in there. So by looking at it, I'm looking for the area, this area between the 2 curves. It's also good with decimals because if you click on this intersection, it tells you what the point is. It tells you exactly what that point is. So I'm just going to take a screenshot of this. And then I'm going to paste it here because so anyway. So that was using decimals to graph the 2 functions. And now I'm going to use a diagram because they give me a visual because I'm looking for this area right here. So this is the area I'm looking for between the curves, right? Obviously from the graph, I already know that I get this point, and then those are the 2 points of intersection. This is the -1, this is 3. If you don't know how to, if you don't use the decimals, you can always find, so note, and find points of intersection by setting the two functions equal by setting 6 minus x squared equals x squared minus 4x. Sorry, not 6. So if you set the two functions equal, solve for x, you should end up with x equals -1 and x equals 3. Those are the points of intersection. But I'm just being a little bit lazy here. So I would say, you know, when you work on homework like this, feel free to use desmos.com to do the graphing. But obviously don't use, you know, don't use other stuff to solve the integration for you. So we're looking for the area bounded between them. And between them, this function, this is a 6 minus x squared, is always higher than the blue line, which is x squared minus 4x. So that means I could just say, okay, I'm going to draw a rectangle here, just get a visual there. So the area we're looking for is equal to integral from a to b. A is -1 to 3, b is 3, of the higher function, which is 6 minus x squared, that's a higher function, minus the lower function, which is x squared minus 4x. So this is the higher function, this is the lower function with respect to x. Now it's with respect to x. I want to emphasize this because next time it's going to be a little bit more confusing if you don't understand what the dx represents. So dx, you can think about is sort of the width of the rectangle delta x. So that's what dx is. So the rectangle I have drawn has the width, has a base delta x, has a height. It's a difference of the two functions. So that's why we have a dx here. And now we just have to integrate this, and that should give us the area. So integrating this, so that gives us from -1 to 3. Just simplify the function before we integrate. So that's a 6 minus x squared minus x squared. So that's a minus 2x squared. Minus 4x, so positive 4x. dx. Could we use decimals on quiz? Absolutely. You know, I don't think that's a focus of calculus. So yes, you can use decimals. It will be great, you know, use decimals, but then on the quiz on your notebook, I'll just sketch what the graph looked like. It doesn't have to be perfect, but make a quick sketch and label those points. Obviously, if you do it on your computer, you can take screenshots like what I'm doing. But if you don't have it, just do a quick sketch. All right, so the rest is about just integrating, I guess. So I'm just gonna, I don't know if I want to go through this, but well, let me do this. So I'm gonna find the antiderivative. So 6 give me 6x. Minus 2x squared give me x cubed 2/3. Plus 4x give me 4. And then x squared divided by 2. And then we're evaluating from -1 to 3. Why is the FH and the FC? Oh, F, sorry, that's not C, that's an L. So FH just means the higher function, the function that's higher. That's what I meant. It's the function like in that region, the higher function, which is the orange line, and then FL means the lower function, which is given by the blue line. The height of the rectangle is always given by the y value of the higher function minus y value of the lower function. That's why I have a, do we not need to add a C? No, we don't, because here, this is a definite integral. So we're looking for values at the end, so we don't need to add a C. If you add it, when we plug in 3 and a -1, the C will cancel anyway. It does no harm, but you don't need to add it. All right. I don't have a calculator, so I'm just going to put in those numbers and leave it there. So 6 times 3 minus 2/3 times 3 cubed. plus that's a 2 times 3 squared, and then minus, putting negative 1, so 6 times negative 1 minus 2 over 3 times negative 1, plus 2 times negative 1 squared cubed. So if you have a calculator, or if you're careful enough with the calculation, you should be able to figure out a number. Does that kind of make sense? So this is one way to find the area of between two curves. If you draw the rectangle vertically, it's always the function higher minus function lower times dx, integrating that to the x boundary. Any questions before I move on to the next part? So I didn't find the final number. Now I want to talk about the next part when you finish taking notes. The next part is relatively easy to understand if what I did now makes sense to you. The next part is drawing the rectangle differently. Instead of using a vertical rectangle, the next part is that if we have a diagram, let's see, we have a function. This is one function. This is another function. Oops. So if you have a function like this, let's call this f, call this g. Instead of drawing the rectangle vertically, I don't need this. So instead of drawing it vertically like what we did before, so the area is equal to, let's call this A, this is a B. So the area we said is integrating A to B f minus g, because this is a higher function, this is a lower function with respect to x. Now, I'm going to draw it differently. I'm going to draw the rectangle horizontally. And if I do that, that base of the rectangle, this part, it's not dx anymore, it's dy. This is delta y that's the base, at the height of the rectangle. And then the horizontal part, the base of the rectangle, is actually given by the difference between f and the g, is between this value and this value. So the area is the same, but the integral value is different. Instead of going from A to B, we are integrating from this y value here to this y value. So we're integrating between those two y values. That's part C and the D. So we're integrating from C to D, but those are y values. Instead of the base of the rectangle is given by the function on the right minus the function on the left. So that's the f minus g, but we use f minus g here because this is the function on the right minus the function on the left. So the L here means left. And then the variable here is not dx, it's dy. So that's using a horizontal rectangle. So this is a horizontal rectangle. This is a vertical rectangle. But I want to point out a couple more things here. You have to be very careful. So the F here, let me use a different color. So this F that we used, it's not the same. It's the same function, but when we put into the formula, it's not going to be the same expression. Because the function we had, this is f of x minus g of x that we're going to put into the formula. But the new one that we're going to use horizontal rectangle is going to depend on y. So we have to use f of y and a g of y. So it probably doesn't make sense to you, doesn't make a lot of meaning to you, but let me use this example to show you and the process. So here's the example I have. I don't know if you notice that we cannot really use a vertical rectangle because here is the same function. So we cannot use a vertical rectangle. You cannot have to find separate functions. So that's a challenging part. So vertical rectangle doesn't work here. Well, it works. It just requires a lot more work. It doesn't work straightforward, like easily here. So we're not going to use a vertical rectangle. Instead, I'm going to use a horizontal rectangle. And this rectangle has a height, delta y. So this is delta y here. And it has a base. The base is given by the value from the black curve, which is x equals y squared minus 4y. And then this x value is given by y equals 2x. So the difference between them will give me the base of the rectangle. So the area for this one is integrating. Now we need to know the two y values as the boundaries. So we need to know the y value goes from 0 to y value that's 4.5. Again, I found this using decimals. I did not do the work. So y goes from 0 to 4.5. Those are the boundaries. The y boundary is not the x. Because for horizontal rectangles, we have to kind of stack up the rectangles vertically. So we need to know the boundaries for y. And here we need to know the function that's on the right, which is the orange one. So we're going to have to use this function y equals 2x minus the function on the left. So this is the right function minus the function on the left, and then dy. And let me rewrite this. So that's a 0. This is a 4.5. What is the function on the right? Well, function on the right is y equals 2x. But that's not, we're not going to put 2x in there, because if we put 2x in there, we cannot integrate with respect to y. So we have to use y. So here we cannot just use 2x here. We have to solve for y. Need a function of y not 2x, not 2x. So how do we find the function of y? Well, we have y equals 2x. So that means we can solve for x. So x equals 1/2 y. So that's what we're going to use, 1/2 y. Now let me use a different color to show that. And then the function on the left is already given in terms of y because it says x equals y squared minus 4y. So y squared minus 4y. We're just going to use it directly. And then we're integrating with respect to dy with y. So with respect to y, so dy. Let me pause here because the rest is about integrating just like we have done before, plugging values. But I think the setup here could be really confusing to you if you haven't kind of fully understand what I did in parts of that formula yet. So let me pause and then let you look at it and then maybe ask questions. Because after you set it up correctly, the rest about solving it, it's a lot easier. So now we take the end exactly. So right now, so the next step is, just simplify the function in the middle a bit, distribute the negative, and then find the antiderivative, and then plug in y values directly to evaluate. It's the same thing as we have done with some fundamental theorem of calculus part 2. But the key part is that it's about setting up the area formula correctly using the horizontal rectangles. So that's the two left and the right rectangles. We have to talk about this because next week we're going to talk about how do we find the volume when we rotate take a function. We take the area, we rotate it along around certain axes. We can find the volume by either rotating it horizontally or rotating it. This is rotating horizontally or rotating vertically, depends on the axis of rotation. So try to make sure you are comfortable with using both horizontal rectangle now and the vertical rectangle to find the area between curves. Any questions on this last part? Next time when we meet, I'm going to go over one example on this, just kind of emphasize those two concepts. Okay. All right. I don't have anything else to say. Well, this is week 1. We have 9 weeks left. So the next step is 1/2 y times. Oh, the next step. Let me write down the next step quickly. So the next step is you still have integral 4.5. I'm just going to drop the parentheses in the middle. So we get 1/2 y minus y squared plus 4y dy. And then if we find the antiderivative, so that will be from 0 to 4.5, the 1/2 y give you 1/2 y squared over 2. Sorry, find antiderivative, don't need that. Minus y squared, so that's a y cubed over 3, 1/3, plus 4y squared divided by 2. Oh yeah, sorry. Yeah, Sam, that's right. And also Daniel. Yeah, both of you were right. I didn't do the calculation. I didn't simplify those two together. Absolutely. So if you simplify them together, you get 9 over 2y minus y squared, and then you're integrating that. Absolutely. Good. All right. On that note, I'm gonna finish it here. Any questions before we end the day?